So this Heathkit IO-18 scope, unlike my IO-102, of which there's a video elsewhere on the channel, this one was not part of my original test equipment back from the early 1970s. This was actually an eBay find, and it was listed as totally untested as is and so forth. In this video, we're going to just do an evaluation of it. We're going to look around inside, see how it's put together. We'll actually turn it on and see how it works, but we won't do that for very long because we don't know what state things like caps and the rest are in. The reason I got this scope is several-fold. First of all, as you'll see, we'll go into a little bit of the history of this last few tube-based scopes. So this was the immediate predecessor to my IO-102. Yet it was the last one of the tube-based oscilloscopes, but it was the first scope that used the new look industrial design, as you can see from the knobs on the front here. And since all of my test equipment uses pretty much that design because it's what I grew up with, that was what made it appealing to me. Also, like the IO-102 and IO-17 and IO-21 and some of the others I'm going to work on, it's dirt simple. So this has no triggered sweep. It's recurring sweep. It doesn't have calibration as you would have in a normal scope. It's single trace. If I don't, obviously, when I restore this, I'm not going to be using it as a daily driver for doing serious troubleshooting. For that, I obviously use a modern scope. So, but I like the fact that this one's dirt simple, like the IO-102 and the others, because frankly, it makes it a lot easier to fix and troubleshoot and fix when something goes wrong. So they're pretty simple scopes, and I kind of like that. I'm probably not interested in getting anything more modern in the Heathkit line or later on in the Heathkit line past the IO-102. The IO-100 series, in my view, was the last of what I'll call the quality solid-state scopes, and then Heathkit would transition to the IO-4000 series, and the quality of the design and materials started taking a nosedive as it the handwriting started becoming more apparent on the wall. So after a couple of tube-based scopes, I think I'll hang it up and go on to other Heathkit goodies. So without further ado, let's take a look at some of the history of these scopes, and then we'll get right into it. So reading from Chuck Penson's Heathkit Test Equipment Products book, which is basically the Bible of all Heathkit products that were ever made. Here's the appropriate page. There's our IO-18 on the top, and its immediate predecessor, the IO-17, and then the IO-21. So Heathkit did not number things in numerical order. It says the IO-17 was a restyled IO-21 with some updates. And it was, if you look at the dates, the 17 and 18 were introduced in 1968 and were both discontinued. Well, the IO-18 was discontinued in 71, the IO-17 in 1972. So both the 18 and 17 were the immediate predecessors of the IO-102 here, which was, of course, the first solid-state general-purpose oscilloscope, which is the one I had from again the early 70s, and these two were the first. These were tube-based, but these two, the 17 and 18, were the first two they were the last of the tube scopes, and the first two that used the Heathkit's new look, as it was called, industrial design. So here I'm showing the 60 hertz line frequency output, which the 1 volt peak to peak, which the scope makes available, directly going into the vertical. I've chosen the lowest possible frequency of sweep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's a sweep frequency of something like 5 or 6 hertz. But the reason I brought this, I have it displaying this way, is because there's a slight non-linearity in the sweep. If you notice that from here to here, the cycles are much closer, not much, but a little bit close together than they are here. So the sweep is not a perfect triangle wave. And in the past, I found that that is usually can be rectified by replacing the one capacitor which selects that particular frequency when you adjust the sweep frequency. Now there's a capacitor for each one of these settings, and the lowest one in this case I think is a 0.2 paper capacitor, and I think replacing that will make that nice and linear again. Right now it's running at full line voltage, and that's fine for now. I don't want to run it like this too long because I haven't recapped it yet. I really don't know what state, how long these caps are, what state they're in, or I don't want to sacrifice my power transformer if one of the main filter caps should short or something like that. So we won't run it that way too long, but we will, let's make sure everything works here. So yeah, the frequency fine adjust works. So now we're sweeping at I guess 30 hertz, and the sweep range ranges from nominally 10 all the way to a nominal 500,000 hertz. You can even detect a little bit of the nonlinearity between the size of these two cycles on the lowest one. So that cap will be replaced. Going top to bottom, we have our usual intensity. Nice, actually it's a nice bright CRT, so that's nice. Intensity, focus, vertical position, horizontal position, all that seems to work fine. Again, the main frequency selector, horizontal and vertical and horizontal gain, those work fine. This frequency selector has a lot of positions on it. So there's 1, 2, 3, 4, 5, 6 positions to select, or 5 positions, 2, 3, 4, 5 positions to select discrete frequencies, which you can fine tune here, sweep frequencies, but there's 4 other positions of this switch, and going from the bottom here, you can select external input, and that's if you want to basically go into XY mode, you connect something here. You can also select line frequency, and so this basically takes another winding off the power transformer and effectively feeds it into the horizontal. And so if you're taking another winding here feeds into the vertical, another winding feeds into horizontal, you wind up with the same frequency at the sine wave at more or less sine wave at both. This isn't a perfect sine wave, and that's why this is not a perfect ellipse. And you get a Lissajous pattern, but basically a circle or a straight line depending on the phase. And that brings us to the phase control here. This is the first time I have a scope with a phase control. And the idea here is if you're in this mode, you can adjust the phase of the line frequency signal that's being fed to the horizontal. You can adjust the phase of that. And so when the two are perfectly in phase, you basically get a diagonal line. But that lets you adjust the phase of the 60 hertz being fed when you're in line frequency in. Then there are 2 presets, preset 1 and preset 2. These do not respond to this fine-tuning control. Instead, they have their own fine-tuning potentiometers, which are behind these 2 little holes. And I believe this is I know one of them is the lowest frequency because it's again the same as this, but then there's this, and this is a higher one. I don't know which one it is, but it's probably like 1,000 hertz or something like that. 1,000 to 10 kilohertz would be my guess. So I guess you could set preset 1 and preset 2 to your favorite sweep frequencies that you want to refer to often. That's basically it. An attenuator here. And the level of external sync you want, you can set here, as well as do you want positive or negative sync. So if we go back to here, turn up the gain, turn up the frequency a little bit.
Come on, go back to more gain. We can have the sync signal can either be positive, it can sync on the positive or negative going half of the cycle, or of course external sync, or of course line frequency sync. Line frequency sync is the same here as the others because of course we're just looking at line frequency. And that in a nutshell is basically the controls of this IO-18.
Quick look at the case. The case is in actually very good shape. So yeah, there are a couple of scratches, but that's part of the character of it, I guess. So it's certainly nothing that would make me want to strip it and repaint it. It's in nice shape. The feet were there. They're in great shape. So that's not a big deal if they weren't, but it's always nice to see that I don't have to replace those. The rear of the case has a little hatch here. That's so you can get into the scope's Z input, which is on the back on the rear chassis. And here's the hole where the power supply and line cord came in. Interesting, the case did not come with a handle, which fits on top, and that annoyed me. So much so that I went out and splurged on eBay and found well, it's upside down, an original Heathkit handle, which would fit Heathkit Precision, and that's shined it up, and that just made me feel better before I even look at what shape the scope's in. And finally, when I looked at the back inside here, I saw this splotch, which originally looked like a burn mark, but then I realized what it is, and what it is, it's not a burn mark. It's when they painted originally the case, the rear of the case, of course, the spray came through the hole, and so this is overspray from the original building of the case. I thought that was amusing. Anyway, case in great shape. Happy to see that. Always happy to see that.
So let's see what we have to work with here, starting on the scope's right-hand side. There's obviously the CRT. Here we have a 6AB4. This is acting as the vertical preamp, vertical input preamp, if you will. And behind there, it looks like a little 100 mic at 50 volts electrolytic. Apart from that, some plastic paper capacitors. I'll have to take a look at those. Moving further back, we have a 6CA4. This thing, along with a little 1V2 all the way over there, is part of the power supply, part of the high voltage power supply, and low voltage power supply. The whole scope is built on a combination of 2 circuit boards and point-to-point wiring, so we have a little bit of everything. We have our main electrolytic multi-section can here, and let's take a look what we got here. This is a combination 40, 20, 20, and 50, so it's a 4-section electrolytic. And I haven't looked at the voltages, but that's okay because whatever we replace it will be far more better than and uniformly what we expect to see here. So that will be replaced by something, perhaps an adapter cap of some kind. We'll see. Moving right along, we have a 12B. So we have 2 tubes here and 2 tubes in the back. These are basically the horizontal and vertical amplifiers that feed the deflection plates of the CRT. Now that's it for the right-hand side. Let's move on. On the back here, we of course have our fuse and line cord and blue and white label. But the back of the smaller of the 2 circuit boards is the one that holds most of the horizontal and vertical amplifiers to the deflection plates. There's the CRT socket. By the way, the CRT here is a 5UP1, which I believe is a bit of an earlier CRT than the IO-102, which is also a 5-inch scope, the transistorized one. The IO-102, I believe, was a 5DEP1. This is a 5UP1. Apart from that, on the back side of the circuit board, most prominently, we have a binding post for the Z-axis. This is where you can connect an external blanking signal if you wish. So if you're using the scope in XY mode, basically you can feed a blanking signal in here to modulate the CRT intensity, or turn it off, I suppose. Another interesting thing is these two wires here, which are going directly to the tube, marked CRT 6 and 7. These are going through two little coils, and these are directly feeding the horizontal deflection plates. So we're going to be careful not to touch those, because those, whatever those coils are, of course, have status of unobtainiums. And in fact, they're coils that are wrapped around resistors, looking at it carefully. So yeah, we're going to leave those alone. But that does it for the rear. And the scope's left-hand side, starting from the front, we have our combination intensity control and on-off switch. We have all the front panel potentiometers. Those two potentiometers that you see down there with little slots in them, those are actually accessible from the front of the scope through tiny holes, and those are fine adjustments for the two preset sweep frequencies that you can choose from. So there's two fairly low frequency presets, and these are their fine adjustments. The main frequency selector switch here is switching in a bunch of different caps, and in particular the lowest frequency one is this 0.2 here, and I think I'm going to replace him because I noticed some nonlinearity when showing like multiple cycles of 60 hertz at the lowest frequency, and that's typically, I found, when it's time to replace this guy. Apart from that, this is the sweep area, the sweep generation area, of course. And conveniently here, this is an electrolytic. It has a convenient feature that it's the cardboard tube that it's built into. You can rotate independent of the capacitor guts, and so that means you can read the value no matter how it was installed. Anyway, this is a 40 at 150, and of course will be a candidate for replacement. Other big plastic paper cap here, and then yes, another multi-section electrolytic, and I'm looking at it, and this looks like a 3-section 20-20-20. And notice it's not on the chassis, it's on the circuit board. So we certainly won't use an adapter cap or anything like that to replace it, but we might just stick 3 axials standing up and have them sitting on the board. That shouldn't be too hard to replace. Apart from that, going on the rear, again, here's our main amplifier board for the deflection. Yet another tubular electrolytic and a cardboard sleeve here. I won't even bother looking at it right now. There's our main multi-section 4-section cap, which we will replace likely with an adapter cap. And I won't go into the tube complement for the sweep, but this last tube here is a 1V2. And this, as you'll see in a minute, as I'm going to digress a little bit on the 1V2, it's our main high voltage rectifier, basically.
I wanted to digress a little bit regarding the 1V2 tube in the IO-18 scope, which of course, as you see here, is a half-wave rectifier. For a few reasons, I found this tube interesting. First of all, in its name, 1V2. One, because it operates at rather low voltage, around 1 volt, in this case less than a volt, as we'll see in a minute. So its filament voltage is on the order of a volt, but in fact less, so that's the 1. Interestingly, the 2 in 1V2 is because it only has 2 elements. It has a directly heated cathode and an anode or plate. So it is, I guess it's arguably the simplest possible vacuum tube that does anything useful at all. And of course it's the equivalent of a solid state diode. If it was a 1V1 any simpler, and I guess that would describe a 1 volt light bulb, I suppose, or a 1 volt heater that does nothing else. So it's I guess the simplest possible vacuum tube. Let me know if you disagree or if you find something simpler. But the other reason is that when I was looking at the spec sheet, so it says filament electrical general data voltage for the filament is a nominal 0.625 volts. So that's what you're supposed to feed the filament. Of course, you then bias it to a much higher voltage, which is what you're actually intent to rectify. But the filament itself, the potential difference between the two ends of the filaments should normally be 0.625. That's great. But I noticed there was a little asterisk next to voltage. And notice the filament says coated. We'll get back to that. So let's look at what the asterisk says. And we scroll down, and the asterisk says, under no circumstances should the filament voltage be less than 0.525 or more than 0.725 volts. So obviously a maximum makes sense, because if you exceed the filament voltage, you'll probably you'll burn the filament out. But why the minimum voltage? And I thought I'd say, okay, that's likely because the filament is coated, and whatever it is the filament is coated with is that which actually generates the electrons for the tube, and I guess it wants to run within a very defined temperature band. In other words, if you run it too cold, or too cool, I should say, I suppose it might get damaged. So I thought I'd do the math, and let's assume 115 volts AC nominal line voltage, because the filament voltage in the scope is, of course, derived simply from a winding of the line voltage transformer. So it's proportional. So let's assume 115 volts AC nominal line voltage, which is what was common back then in the early 60s or 50s, perhaps, when this was invented. In any case, we'll go with that instead of 120. So if you do the math, if 0.625 is the nominal at 115 that you're supposed to use, well, 0.525 would equate to about 97-ish volts minimum line voltage, and the 0.725 would equate to about 133-ish line voltage. So the idea is the scope really shouldn't be operated anything less than 97 volts AC and anything more than 133-ish volts AC. And so that's why when I brought up the scope initially, I didn't just leave it at a very low voltage and gradually bring it up very slowly, leaving it for the electrolytics to do their thing. No, none of that. I basically just brought it up at a reasonable speed. I didn't want to slam it, but then I left it at 115 volts while I was looking and playing with it. So anyway, I thought that was an interesting digression regarding the 1v2. But wait, there's more regarding the 1v2 in the IO-18. So here's the IO-18's power supply. And just starting at the bottom here, we have a 6.3 volt winding for all of the tube filaments, except for two other tubes. So here's the tube for the rest of the non-high voltage stuff coming that the scope needs. But here's our 1v2. And the 1v2 filament is fed off this tiny little portion of a winding, which I guess develops 0.625 volts. But of course, it's part of a much higher voltage winding, and that's how we derive the very high voltage DC here, which goes off to the focus, intensity, astigmatism, all those controls, and the cathode get fed by that. So that's our 1v2. What's very interesting is Heathkit must have done a redesign of the scope, because when I was looking up schematics before I got a manual, obviously I found this, but I also found this, and this is the IO-18U. U, I suppose, as in updated. And I actually found a manual for this, but there are a couple of changes they made. They made some structural changes in the metal work. They did a few things. For example, this other rectifier tube here has now a split cathode. But look, our 1v2 is simply gone. It used to be here. Now it's gone, and it's of course replaced by a solid state diode. So I found that interesting. Perhaps, as the IO-18 was transitioning, as Heathkit was transitioning from tube-based scopes to full solid state, as in my IO-102, which was the first of its kind, they found that maybe not. We won't use a 1v2 anymore. We'll start with a high voltage diode here, and that's what they did. And by the way, that's also what they did on the IO-17, which only had one variant, and of course started out with a high voltage diode, but was otherwise tube based. So I thought that was interesting. Heathkit decided that the first tube they should get rid of in their scope design as they were transitioning would be the 1v2.
And that does it for the scope's left-hand side. And here's the underside of the IO-18. You wanted point-to-point, you got point-to-point. This is where it's mostly at, for that which isn't on a circuit board. Starting on the back, we have our usual two high-voltage caps. These are likely 0.1s at 1600. These, of course, do get replaced because they do. I have seen these fail, particularly in my IO-102. Apart from that, this pot here, I haven't looked, but is likely the astigmatism control because the focus is on the front, and this is the only other thing that you can adjust. Plus, it's right next to the 1v2 high voltage section here, so that's probably what that's doing. Here's the underside of the circuit board. Here's the underside of the multi-section cap. We will have to be careful when we unsolder this. It's going to be a pain because there's a lot of solder on tabs here to get rid of. That's not going to be fun at all. Plus, when we replace it with discrete capacitors, we're going to have to keep in mind that it appears that the case tabs of the can are also being used as effectively ground jumpers to connect the traces on the board, which would not otherwise be connected, irrespective of the capacitor. So we have to be careful and make sure we complete those circuits as we remove this and check it against the schematic. Apart from that, more plastic paper caps. There's our trusty pilot light. Works fine, not going to touch it. Here's our vertical input compensation trimmer capacitors. Those I didn't check, but I don't have any reason to think that they won't work. The selector switches in general, we're going to deox them a bit and clean them up, but I didn't see anything hard there. And of course, our main power transformer. So that's the underside. I'm really not looking forward to having to taking this can out, but we'll see.
So that's about as far as I can go on this part. So I'm going to cut it off here, and there'll be a part 2 eventually. But first I have to spend some quality time with Mauser to get some more parts that I'm going to need to clean this scope up. I did notice I had still a little bit of a stash of skinny electrolytics, almost enough to replace the two multi-section cans. The larger one is the 40-20-20-50 at 450 and 300, and for that's the one that's chassis mounted, and for that I'll use one of these Adaptacap-like boards, and I happen to have just what I need here. I think I have all of these everything here is 450. So I have a 47 to replace the 40, and I have two 22s to replace the 20s, and then I have a 39 here to replace the 40, or I could put a 47. So I don't know, which one should I put to replace the 40? Should I put a 39 or a 47? Let me know in the comments. In any case, they'll all fit because there's, well, except for the 50, they're all skinny, and everything fits within the footprint of that little board. And that's how it's going to look. It's going to look very nice. For the other multi-section can, which is a 3-section can, which is 20, 20, 20 at 250, 250, 250. Again, these are all 450s here. I think I'm going to be short a 20, so I'm just going to borrow this 20, one of these 20s here. And for this, I'm not going to put them on a board. I'm just going to probably silicone them together. I was going to use axials, but no, might as well use radials, and poke these through the holes where the can was, and set up the ground connections just the way they should be, and that should be just fine once these are siliconed into a little. Try it here. So anyway, that's it. We'll see you again on this project when I've got more parts in.